Hello friends, welcome you once again. So in this video I will discuss about the PN junction. Basically in the previous video we have discussed about the silicon and the N-type and P-type semiconductors. So in this PN junction we have two types of silicon, the P-type and N-type come at an interface. So this is the interface basically. So whole the phenomena will happen only at this junction, and this is called PN junction. Now in the previous video, if you have watched, I have discussed about the diffusion. So basically diffusion happens due to the concentration profile. So if we have this type of charge concentration, यहाँ पे चार्ज है, यहाँ पे डिस्टेंस है, तो इसका जो ग्रेडियंट होगा ना, ग्रेडियंट विद रिस्पेक्ट टू डिस्टेंस, ये क्या करेगा, करंट फ्लो में, चार्ज फ्लो में कंट्रीब्यूट करेगा. तो अगर इस जंक्शन पे देखें, यहाँ पे जो पी टाइप सिलिकॉन है, तो यहाँ पे क्या है, होल्स की कंसनट्रेशन है, इलेक्ट्रॉन की कंसनट्रेशन से काफ़ी ज़्यादा है, और यहाँ पे जो हाई कंसनट्रेशन हो इलेक्ट्रॉन्स की है और लो कंसनट्रेशन की होल्स की है. तो होल्स के लिए जो कंसनट्रेशन प्रोफाइल बन रही है वो ये बन रही है. होल्स के लिए जो कंसनट्रेशन प्रोफाइल बन रही है ये बन रही है. बेसिकली अगर इसको हम जूम करें तो ये बन रही है. तो यहाँ ड्यू टू दिस ग्रेडियंट ना, यहाँ से होल्स क्या करेगा, इधर डिफ्यूज करेगा. और सिमिलरली अगर इलेक्ट्रॉन का कंसनट्रेशन प्रोफाइल अगर हम देखें तो ये मेरा ऐसे बन रही है, राइट. सो ड्यू टू दिस यहाँ के कारण, इस कंसनट्रेशन प्रोफाइल के कारण डिफ्यूजन जो चार्ज होगा ना, डिफ्यूज करेगा. तो यहाँ से इलेक्ट्रॉन क्या करेगी, यहाँ पर डिफ्यूज करेगी. लेकिन यहाँ जो इलेक्ट्रॉन डिफ्यूज कर रही है ना, कि चूँकि मेरे पास पी टाइप सिलिकॉन में ना होल्स की कंसनट्रेशन काफ़ी ज़्यादा है, तो यहाँ पे क्या होगा ना, जस्ट इसे क्रॉस करेगा ना जंक्शन को, तो रिकॉम्बिनेशन प्रोसेस शुरू हो जाएगी. तो रिकॉम्बिनेशन प्रोसेस में क्या होता है, जो इलेक्ट्रॉन है एंड होल है वो आपस में फिर से मिल जाती है एंड एक बॉन्ड बना लेता है. तो बेसिकली क्या है कि ये both charges are no more in the conduction band, they have moved to, you can say, valence band. So ये जो रीजन बनेगा ना, यहाँ पे रिकॉम्बिनेशन जो होगी, तो रिकॉम्बिनेशन के कारण एक फिक्स चार्जेस बनेगा. और ये जो रीजन है ना, ये हाई रेजिस्टिविटी रीजन है, और यू कैन से इंसुलेटेड रीजन है, राइट. और ओके, सो दिस टाइप विल हैव, यहाँ से जो होल्स है यहाँ पे आके क्या कर रही है, रिकम्बाइन कर रही है और फिक्स हो जा रही है. तो यहाँ पे जो इस साइड में जो मेरा चार्ज का जो कंसंट्रेशन होगा, ये बेसिकली इस होल्स का होगा. पी टाइप की जो होल्स आ रही है वो इसका होगा, तो ये पॉजिटिव चार्ज बनेगा. और सिमिलरली यहाँ पे जो इस साइड में आई क्या होगी, इलेक्ट्रॉन्स आके रिकम्बाइन हो रही है. और यहाँ पे जो चार्ज होती है ना, इसको बोलते हैं अनकवर्ड चार्ज बोलते हैं. क्यों? क्योंकि यहाँ से जो इलेक्ट्रॉन आ रही है ना, वो इस होल से न्यूट्रलाइज नहीं होती है, क्योंकि वो फिक्स हो जाती है, राइट. और इस रीजन को ना, इस स्पेस चार्ज रीजन को क्या बोलते हैं, स्पेस चार्ज रीजन बोलते हैं, और कैरियर डिप्लीशन रीजन भी बोलते हैं. तो ये चार्ज एक्युमुलेशन के कारण, अनकवर्ड चार्ज के कारण मेरा एक इलेक्ट्रिक फील्ड क्या होगा, इलेक्ट्रिक फील्ड यहाँ पे जनरेट होगी, जिसकी डायरेक्शन पॉजिटिव साइड से नेगेटिव साइड होगी. और ड्यू टू दिस इलेक्ट्रिक फील्ड अगेन वी हैव another kind of charge flow that is called the drifting, or you can say drift current. So how drift current? Now once again I am mentioning that this diffusion due to this charge movement, due to this diffusion generate current which we denote with is. Right, now come to the drifting. So let's see from the inside silicon. Here we have holes as minority carriers. So here somehow these holes move, or say these holes move to this interface. So these holes will be swept with this electric field to this side, right. and again electrons from this p type which are minority carriers will be shift to this side due to electric field. As we have studied, the positive charge move in the direction of electric field and the negative charges move in the direction opposite to the electric field. So this minority carrier or charge movements create current which we will denote by ID, drift current. And due to these two process, this voltage difference won't exceed after some limits, and this voltage, the equilibrium voltage, what we called as barrier voltage, also called junction built-in voltage. Let's see what is the formula for the junction built-in voltage. So junction built-in voltage is denoted with the V naught, and it is Vt, natural log of concentration of acceptor atoms into concentration of donor atoms. So this is the p type. It basically accepts the electrons and create the holes. So this concentration, atoms of this concentration is nothing but the Na, and here the donor, electron donor atom concentration is Nd. So these products divided by Ni का whole square. So ये जो टाइप के इसकी जो वैल्यू होती है ना, ये होती है 0.6 to 0.9 वोल्ट ना. अगर देखिए यहाँ पे तो Vt जो होती है ना, वो क्या होती है, KT/Q होती है. तो बेसिकली जो ये टेम्परेचर डिपेंडेंट है ना, सो जंक्शन बिल्ट इन वोल्टेज आ जाती है, टेम्परेचर पर डिपेंडेंसी इसकी आ जाती है, एंड डोपिंग पे इसकी डिपेंडेंसी होती है. ओके, नाउ लेट्स सी अबाउट द विड्थ ऑफ दिस इज वेरी इंपॉर्टेंट. नाउ विल सी अबाउट द this charge stored in the depletion region. So as you can see, here we have a p type and here we have n type silicon. So here its concentration is Na divided by Na, means the concentration of acceptor atoms, and here the donor atoms. Now as you can see, the depletion region have less deeper depleted inside of the Na, because the practically what happens that the concentration of the acceptor atom is much greater than the Nd. So this side in the less area we get the same amount of charge as in the donor side. Basically both the current are in the equilibrium, so the charge flow from one side to other are equal amount. So that's why if this is depleted more, so this will be lightly depleted, means less depleted. So here we will denote by the xp and here by the xn. Then the, and as you get its area now, if you really take the slab, so this is the p side, this is the n side, and if you visualize in 3D, so this is the area basically. So if this is the area, then what is the charge here? Charge here will be q plus will be area into xn, right, into Nd into the unit charge. This will be converted into the coulomb, and this total will convert into the number of charge entities, like so. As you can see, the concentration profile, the concentration of the acceptor atom is higher than the concentration of the donor atoms. Hence again, if we use the formula of our first video or second video, I think, so this will be the N square. So this will be the minority charge here, the holes in the these Nd region holes, and similarly these are the electrons in the p-type regions, or this will be the magnetic carriers, or this is the majority carriers here, this is the magnetic carrier here, like electron is a minority carrier here but majority carrier here. Now these are basically the conducting elements, the p-type and type are the conducting elements, these two. So if this will be like, this is the negative, so if you treat this as zero potential, so this is the holes, so this will be a higher potential than this, so our voltage, the V0 will have this like curve. So this will be the p side and this will be the n side, right? So this built-in voltage, bias voltage, built-in voltage, junction built-in voltage is directions. Now so here there will be charge density, so this is the what we have written here, so this is the charge holes and this is the electrons. Now the channel width, here the depletion channel region width is denoted by the W, and W will be equal to Xn plus Xp. And remember this formula, we are not going to derive it here, so this is important formula, it is under square root of 2 epsilon nets. This is the silicon electric permittivity, and this is the charge, unit charge 1.19 coulomb, and this is the concentration of acceptor atom, concentration of donor atom, and this is the junction built-in voltage V0, right? Now as you can see here, and if you write like Q minus, then it will be An into Xp into Na into, this is the concentration here Na, and into Q, because this charge will be in the same concentration as of Na, right? Here once again the holes this holes charges concentration will be same as this, because this has been formed after the depleting the charges, these electrons, or here in the reverse, vice versa. So these two charges are equal because the current flow from both sides are equal, so this Q plus will be equal to Q minus. So if you equate now, then this A will be cancelled, so we will get Xn into Nd equal to Xp into Na, or Xn divided by Xp is equal to Na by Nd, right? Now from this we can derive these two equations. How? If we add 1 to both the sides, so this will be Xp Na plus Nd divided by Nd, and this is nothing but W, so we have Xp is equal to, this will go this side, W into Nd divided by Na plus Nd. So this is the formula we have written here, and this is the same thing. So from these equations, we can write Qj also here, Qj. So how we can write Qj? So the junction charge will be either equal to Q minus or Q plus. So if you write Q plus, the Q plus we have written A into, let's sum up, Xn Nd into Q, right? Let's use the Q minus, that will Xp Na, because we have the derived here, so it will be A into W into Nd here, from here Na divided by Na plus Nd into Q, right? So this is basically the here written junction charge. And W here you have to just remember the formula for the W, depletion width, so you have to remember this. If we put this value here, then we will get what is called the charge stored in the junction. So this will be here, this is what we get. So you can remember this. We will use this formula in the calculation of junction capacitance of the diode. Now coming next, if we apply the voltage, then what will happen, right? So if we apply voltage to this junction, so let's suppose we are reverse biasing. Okay, suppose we are reverse biasing. So reverse biasing means this will be connected to negative terminal, then so this, in this way we will connect. So already this was negative, now due to this applied potential this has become more negative. So more negative, so this will do what? This will increase the electric field, right? Because now the voltage we are getting is V. If this is V, then it will be V naught plus V, because this reverse voltage is getting added. So due to this, if the electric field increases, then drift current will increase, right? Drift current will increase, as I have already told you. So what will happen? This minority electrons, this minority holes here will drift here, and similarly the minority holes will drift here. So more drifting will happen, and this depletion region will increase in both the directions. If we more increase the voltage, then the diffusion width will increase more. So here we can replace this V naught with the formula in case of reverse biasing, right? So channel width will be gained by this. I already explained you how this will be increased. Now let's suppose we are forward biasing it, right? So in the forward bias, this will be connected to the positive terminal, and this inside will be connected to the negative terminal. This is the symbol of the diode. So now what will happen? This depletion, let's forget about this. So now you can see that the diffusion will happen due to this concentration profile, already explained you previously upper. So now due to this positive terminal, currently the voltage profile was something like this. This is the other region, then we have something like this, V naught, right? So this V naught will decrease. Now if the V naught will decrease, then the drifting, then this what is called depletion interval will decrease, because we have the electric field is now less. The electric field strength has been less, so less amount of drifting will happen. But this is the diffusion, because drifting has been decreased, so the concentration profile of the holes here has been increased, right? So the more holes will now diffuse. Once again, due to this depletion region has been decreased, so the whole electron concentration has been increased, because this length action has been now come here, so more electron will diffuse, so the diffusion current has been increased. So the ID had been increased and IS had been decreased, right? The drifting current has been decreased, but the diffusion current, so this will contribute so the electrons of this will pass through this and will be collected by this here, and similarly holes will come and will connected by the negative terminal. So this both will constitute the current, which we call the diode current, right? So this is what happens in the forward region. Now for the forward region we have a formula of for the current, which is given by ID is equal to IS e to the power V divided by Vt minus 1, where V is the applied voltage and Vt is the thermal voltage, Kt by Q, and we will see it later in this video only. Now coming next, this I have already explained you upper. So this will be the formula for the width of the depletion region, and this is the charge stored in the depleted region, and this is current relationship. So how this relationship we get actually? So already told you that this current will be due to the diffusion region, right? Because the concentration profile has been increasing. So from the physics we get something like some equations of P, like concentration in terms of E, something like this, P naught. So already we have explained in the diffusion current video that the Jp, current density Jp for the holes, is given by Q dp on the derivative of the, or you can the slope of the px curve. So this after doing this calculation we will get this, what we will get, this one. Add both the side for the holes and electrons. So this is for the holes and this is for the electrons. So we will get this formula, and this we call as, we denote by Is, which is called as the saturation current, or also called a scale current. This n denote means that I am reading this, or a scale current. As you can see, this is 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 proportional to the junction area and also proportional to Nis square, means this is the strong function of temperature. So Is is also a strong function of temperature. Now let's come discuss this point, breakdown. So if we already reverse biased, so if this is the diode, and now if we are connecting this to negative terminal, so if you are biasing this, then this is called the reverse bias. After this voltage reaches this Vz, this is called the Zener voltage. It is mentioned in the specification and denoted by Vz only on the device specifications mentioned by the manufacturer. So once this V is reached now, then see the Vz is almost constant. There is no increase in the voltage, but there is a large increase in the current dramatically. So this phenomena is known as the reverse breakdown. And there are two ways. When this voltage is less than 5 volt, then the effect is due to the Zener effect, and when the voltage is greater than 7 volt then it is avalanche effect, and if the breakdown happens in between, then the phenomena can be due to both. So in the Zener effect what happens that the electric field, the applied electric field, and this is the depletion region, has been increased such that the covalent bond of the silicon gets breaked. Okay, and if this is p side, this is n side, so electron from this are collected here and holes from here are collected here, because this, am I right? No, these holes will be collected here and this electron will be collected here. Okay, after the breakdown. In the avalanche effect, what happens if we come up now, let me explain deeper. So we are basically reverse biasing it. So in the reverse biasing, what will happen, let's see the drift, this electric field will increase, right? So that due to increase in the electric field, the process of drifting will be more frequent, right? The holes from this will drift and electron, this drifting host electron will have sufficient energy to break down the covalent bond. So due to breakdown due to this moving charge carriers, no, so in the p side and the breakdown will be due to the electrons, and the n side breakdown will be due to the holes. So this type of breakdown now is called the avalanche breakdown. So this is what I mean. If we have breakdown happens at higher voltage, then the avalanche effect will come in role play. Now let's come to the capacitive effect. Now capacitive effect we have in the junction, we have two type. One is the junction depletion, and the other diffusion capacitance. In the depletion, what happens, we have already derived the formula of Qj. Now we know that Q is equal to Cv, so the capacitance C is equal to dq by dv. So once we differentiate this Qj, then we will get what is called, I have not written here, so we will get some equations that will be like Cj is equal to Cj naught root over 1 plus Vr by V naught. This is the reverse voltage, and this is the built-in voltage, junction built-in voltage, and this Cj naught, no. So how we will differentiate it? So first differentiate it, I will upload it and discuss it my another video, in my another video, to how to find this junction capacitance. So this video I think I should end here because this has become so large. So thanks for watching, guys. Have a nice day.